Thank you very much, everyone, for being here. My name is Carlos Perez-Delgado, and I'm going to talk about what is a quantum computer. So before I introduce myself, why do we even care what a quantum computer is? Here's a few news pieces that I've taken off the web in the past 3 months. This is the beginning of 2018, and it refers to large, important companies that we all know about: Google, IBM, Intel, NEC. They're all jumping into this area of quantum computing. They're pouring millions of dollars, millions of euros, and millions of pounds, and they're getting there. They're achieving very important stuff. Now, who am I? I'm a lecturer here at the University of Kent in computer science. I have 10 years of experience working on quantum computing and quantum computing research. I have a PhD from the Institute of Quantum Computing at the University of Waterloo in Canada. I worked for a while at the Center for Quantum Technologies at the National University of Singapore in Singapore. Now, the reason I say all this is to make it clear to all of you here in the audience and at home that I'm not going to lie to you. Everything that I say here is going to be perfectly accurate. Now, I will simplify stuff. You won't see any mathematics up there, and this is a very technical subject. But what I promise is that I will simplify as much as I can, but no more than that. So let's get started. So what is a quantum computer? To understand what a quantum computer is, first we need to understand what quantum theory is. In the words of Richard Feynman, one of the most famous physicists of our time, quantum theory is the most successful theory of all time. It is so successful, in fact, that it is similar in its predictive powers to measuring the distance between Los Angeles and New York down to the breadth of a human hair. Now, all this accuracy has a cost, and the cost has been the erosion of our human intuition. Quantum theory is simply not intuitive. Now, we can summarize the basic tenets of quantum theory into 3 basic tenets. The first one is that both matter and energy behave both like particles and waves. The second is that quantum systems can be in what we call superpositions. These are complicated states. And the best example of this is something that I'm sure all of you have heard of, which is Schrodinger's cat. It's a cat that's in a box, and as long as I don't look at it, that cat can be both dead and alive at the same time. It's not that it's either dead or alive, it's both, or neither. And I'll explain more of that in a second. A third tenet of quantum theory is that when I measure a quantum system, I invariably alter its state. I cannot measure a quantum system without disturbing it. Now let's focus on the second tenet, because we can use that for quantum computation. Much like Schrodinger's cat can be both dead and alive, a quantum bit can be both in the state 0 and 1 at the same time. To remind you all, a classical bit is the essential building block, the fundamental building block of computers. A bit can be either 0 or 1. A quantum bit can be in both. And that means that if I have 2 quantum bits, I can have the states 0, 1, 2, and 3 simultaneously. Let's try to explain this with a little bit of help from some pictures. Think of the Cartesian coordinates, your xy plane, north, south, east, west. Now, a classical bit will always be on one of these axes. So we can represent a bit being in the state 0 by being on the x-axis, and a bit in the state 1 by being on the y-axis. And that's a classical bit. You can only either be on one of those 2 lines, one of those 2 blue lines. A quantum bit, however, can be on a diagonal, and it can be in any direction whatsoever. Important to remember is that if I measure that quantum bit, I'll only ever measure a 0 or a 1. Which one will I measure? Well, if we were to cast a torch from the very top, that line, that blue line, will cast a shadow onto the x-axis. And that shadow that you see there is proportional to the probability of me measuring a 0. Similarly, if I shine the torch from the far right, the shadow that it casts onto the y-axis is proportional to the probability of measuring a 1. So if I measure a quantum bit, I only measure a 0 or a 1. But as long as I don't measure it, it can be in this strange diagonal state, which is neither 0 or 1. We can use these. We can use this power, this quantum computing power, to speed up some computations. The punchline is that you can't solve all problems faster on a quantum computer, but you can solve some problems somewhat faster, and you can solve a fewer problems a lot faster. What are quantum computers specifically good for? Well, they're very good at simulation. They're very good at solving some hard optimization problems, some hard mathematics problems. They're also good at machine learning. And they're also very good at one other thing that I won't mention quite yet. Before I get there, let's talk about the internet. We all use the internet here. We all go online, shop online, go on Facebook, post pictures of ourselves. And we all care about our privacy and the security of our information. And all that information is safeguarded by what we call cryptography. And there's a particular type of cryptography which we call public key cryptography, which is what we use to authenticate people on the internet and to create private communication. By authentication, I mean that you can prove that you are who you say you are. Or for example, when you go to your bank's webpage, you know that that webpage actually belongs to your bank and you're not being scammed out of your money. Together, public key cryptography is used in all sorts of applications, from online banking to your private communication, your email, your RSA, two-factor keys, et cetera, et cetera. Without public key cryptography, literally the internet would stop working tomorrow. Now, public key cryptography, as we know it, is all based on certain types of problems that are very easy to perform, but very difficult to undo. And a good example of that is multiplication versus factoring. If I give you two numbers, for example, 23 and 11, and ask you to multiply them, that's generally easy for you. If you're thinking 253, that's the right answer. But if I give you a large number and ask you what two numbers multiply to that number, that's harder. If I give you the number 221 and ask you what two numbers multiplied together give you 221, that's harder. The answer, by the way, is 13 and 17. It's important to know, though, that this isn't just harder for you and me as people, it's also harder for computers. In fact, the difficulty of factoring, the difficulty of finding the factors, is an intrinsic part of the security of public key cryptography. The most used out there public key cryptographic tool is RSA 2048. It is the gold standard, and it's based on factoring. Now that introduces a problem because quantum computers are really good at factoring. How good are they? Well, let's put up an example. If I gave you the most powerful classical computers today, take your pick, it would take them around several times the age of the universe to break RSA 2048. Again, RSA 2048, it's the gold standard of security today. And the reason is because your classical computers would take millions and millions of years to break it. But a quantum computer, a modest quantum computer, bigger than any quantum computer we have today, but nowhere near as powerful as the classical computers that we have today, that quantum computer would only take 14 minutes to break RSA 2048. So you can see the problem here. Now, fortunately, as I said, quantum computers today are simply not large enough to break RSA 2048. But some of us predict, some of my colleagues and myself, have predicted that there's a good probability that by the year 2030, there will be quantum computers large enough to break RSA 2048. Fortunately, there's a plan. In fact, there's two plans. There's a two-tiered approach. The first one consisting of what we call post-quantum cryptography. Post-quantum cryptography simply refers to cryptographic systems that are not known to be breakable by quantum computers. So there's no attack, there's no quantum computing attack for post-quantum crypto. But another idea is to use the power of quantum theory itself to create security. If you'll remember towards the beginning of my talk, I mentioned how when you measure a quantum system, you invariably alter its state. So I can prepare quantum systems in particular states, and if someone else comes in and observes them, just looks at them, I'll know, because they'll alter its state. It's like nature is providing its very own intrusion detection system. And we can use this. We can use this to build cryptographic tools to regain the security that we'll be losing and create even better security tools unlike you've ever seen before. Now, if you want to learn more about that, you'll have to stay tuned on this channel. For today, that's all for me. Thank you all very much for your attention.